So let me get started. It's really a pleasure to be the seminar speaker of my older department, former department. As Tomek mentioned, I have been one of the early faculty members of that department who contributed a lot actually to the creation of the PhD program and the undergraduate program of that department. I'm so proud of the years I spent there. And I think even though the department is small, but I think it still has tremendous potential to grow. And I think there is a big chance of that happening in the future. So saying this, let me now switch to the topic of my presentation. I'm a computational scientist with emphasis in material science applications and mechanics. My research is motivated by scientific questions related to material science, but I'm also heavily involved in method development. So that sort of comes as a natural evolution from being a theorist and maybe a pseudo-applied mathematics person by interest, but being a theorist, things are now kind of turning theory into predictive tools, and that comes through computations. So I'm a computational material scientist. Our group at Purdue University does a wide spectrum of research activities, all in materials and mechanics, of course, but we go from theory to numerics and computational algorithms to computing, and also recently with the evolution of the fields, also we do data-driven research, or we integrate data science into our research methods. Today I'm going to talk about a method under development in my group, and it's called DFT-Informed Kinetic Monte Carlo Simulation. And DFT stands for Density Functional Theory, and the method itself is Kinetic Monte Carlo. And we apply this to the growth of multiphase films. These are special class of materials that have very thin or small dimensions, and they have a lot of applications in physics and chemistry and so on. The work has been done by 3 of my students with myself. The first one worked on this was Kyle Starkey, who is now a staff scientist at Materials Design Incorporation. This MDI thing is a company that sells the famous code called VASP, the DFT code. Shrikar, and he's a phase field modeler, but he got involved in this. And most of today's presentation is done by Ahmed, who is currently a PhD student. He's a developer of this DFT KMC approach, but these folks worked also on various aspects or mechanics aspects of these thin films. This work is supported by the US Department of Energy, BES, Materials Synthesis and Processing Program, and it's in collaboration with a colleague of mine, Haiyan Wang, who is an experimentalist. So we interact with her and her students on a regular basis to advance this work. So this research is part of a project called Achieving Long-Range Order in Oxide Metal Hybrid Materials. And the systems, as the title says here, we're trying to design these materials in such a way that they have like a film configuration, but the film is traversed by these thin pillars, nano pillars. We call them pillars. They are like whiskers, used to be called whiskers a long time ago, but they are of nano dimensions. You have like a few nanometer diameters, like 3-4 nanometer diameters and so on. And the organization, they are self-assembled in the sense that they grow by just depositing the atoms. And the organization of these does have an influence on the properties. The properties of interest for these things are optical properties, plasmonics, magnetic, and catalysis applications as well. So the high end is the one who grow these films and characterize their properties and so on. We are trying to understand, as a collaborator who's doing theory and computational work, we're trying to understand how these things grow and what gives rise to the self-organization of these pillars in the matrix of the film. Just to let you know the order of dimensions here, the film thickness is from here to the top. This is on the order of 20 to 30 nanometers, maybe 40 nanometers or so. These vertical lighter colors are the pillars. The dark background is the matrix. And we use a variety of combinations of materials to grow these things using pulsed laser deposition. Our goal is to understand the energy or energetics of these systems and kinetics of growth as well. The growth itself is done by this fancy pulsed laser deposition device. I like to simplify to this picture here. It's a chamber that is vacuum, under vacuum, and laser pulses come to a target material that evaporates the material and deposit them on this substrate. So the useful material that we collect comes on this substrate here at the end. Pulse laser means that we send the energy of the laser in pulses, like 5 pulses per second, 10 pulses per second, and so on. Tailoring the energy and the target material gives, the variety of parameters to look at or they control the growth of these films, including the substrate temperature as well. So this is just a schematic of telling us that the materials that laser pulses come in discrete events like this, and then the material that is also deposited on this target, on this substrate, also come in patches, just one patch after the other at a certain drip rate. So the objective for us as modelers is to understand the thermodynamics of these systems. We call it the energetics here for simplicity. And that kind of identifies favorable configurations from an energy point of view. Whether these configurations are achievable or not from an actual deposition point of view, that depends on kinetics. So an early phase of this work focused on the energetics, but today I'm going to focus more on the kinetics of growth of these films. And a different level of modeling would be to look at the connection between the microstructure and the properties. So we're still at the stage of understanding the growth. We haven't shifted to modeling the properties of these films from the microstructure state of the films themselves. So we're here today. Maybe in the future I can do something else with the same thing. In the energy business, we look at the interplay between elastic energy, interfacial energy, and chemical energy in these systems. The elastic energy arises from the fact that these things are made of multiple materials, gray, green, and gold here. And these multiple materials are crystalline, and they do have different lattice parameters. So when you try to fit them together to form a composite material like this, you have to stretch one of them and compress the other, etc., in order to fit them together. That is called lattice mismatch. It's sort of augmented with the so-called thermal mismatch, because when you cool these things from higher temperature and so on, that contributes to that mismatch in a different way. And that leads to elasticity. So these systems store a lot of elastic energy. Together with the interfaces, there is interfacial energy. And then because of composition, they do store chemical energy that can be varied or tailored somehow by the fact that the atomic species are actually mobile or have the freedom to go from one phase into the other. that is the energetic business. Kinetic depends on how we grow, the growth process for these films, and the energy business is part of it. This energy thing comes in, you will see later, it's coming in the bonding of these atoms at different places and so on. So the kinetics does still capture the thermodynamics in various ways. This brings me to the content or the outline of my presentation today, kinetic Monte Carlo algorithm. I'll explain what the algorithm is and then present some results for a system made of gold pillars embedded in Syria matrix grown on STO substrate. And then I'll present the elastic effects within this Monte Carlo framework, and then coupling of the elastic effects with the kinetics of growth. We call this strain coupling with diffusion kinetics. I'll show you this results here and just a preliminary result in this area before I talk about future work. This is the multi-scale framework that we use, if you want to call it so. It consists of the engine here, or the simulation tool is a Monte Carlo framework, but as the film grows, it has elastic effects. We tie those strain effects to the growth through the bonding effect of strain on bonding and hopping energies for atoms on the surface. And these fundamental energies come from density functional theory, through this VASP code. So we have multiple codes and multiple physics here tied together: elasticity, fusion, and bonding, and then the parameterization using electronic structure methods. That is basically the framework. So in this KNC framework, material come in patches. Again, we simulate this deposition as pulses like this with a given magnitude come in time. This is called a Coulomb function or something like that. It's a superposition of just impulses coming in. This is your material deposition rate. And when the material come to the surface, the bond to the surface and the hop from one surface side to the next. So we look at the energetics of this process in terms of two energies that both contribute to the final hopping rate. Those two energies are the energies of hopping, assuming that the material or the hopping species is not constrained by any neighboring atoms, with a correction coming from the bonding at the initial site and the final site here. This you can call the thermodynamic effect, because it's just a term that depends on difference in bonding between places. If this leads to phase separation, this will be basically the energy quantities that give rise to difference in, say, bonding energy or free energy between a mixed state and a phase-separated state or something like that. This is in a simplistic way because we're not considering the finite temperature effects on this, but every energy quantity here comes with the by DFT parameterization at zero temperature. So DFT helps us compute these hopping energies and binding energies. A combination gives rise to the hopping rate. And then because of the heterogeneity of the system, this hopping rate and the bonding energies and so on are actually interpolated in terms of the neighborhoods in there. The hopping process looks like this. You have atoms, they have the freedom to move in various directions on the surface. This motion is later constrained by the atomic neighborhood when the surface layer is filled with atoms. So it's a process that depends on the level of coverage of atoms on a given layer. The probability of hopping is given by this rate normalized to the total rate for a particular process, and these are occupancy numbers on the surface. It is executed through a random number, and the probabilities of an event given that events have not taken place, or so it's just schematic here. So that probability thing gives us the time step, and that's time, the ability to compute time based on hopping rate is what gives the name to the Monte Carlo scheme here, kinetic Monte Carlo. So when we do this, the earlier version of this is just one, you're just represent the surface and look for a given event to execute on the surface. So it's a serial process by nature. Later, in later years, there has been a parallelization or schemes of parallelized Monte Carlo that sort of execute multiple events on the surface at the same time. This is illustrated here by dividing the surface into subdomains, and then each domain is broken into 4 quadrants here. And then you could think of this as an image, but it is not an exact image. And when we do parallel execution, we do search for these events happening in one quadrant at a time that is repeated in all subdomain. And then the next step, we look at another quadrant and a third quadrant and so on. There is a little bit of bookkeeping here because you have to sort of resolve events at boundaries here, but that is sort of taken care of by looking at quadrants and as opposed to events happening place at the subdomain as a whole here. That enables you to simulate larger areas on the surface, and that is important because the time it takes for Monte Carlo to execute can be a limiting factor in studying the system size, and the system size has to be as dictated by the fact that you need to resolve certain microstructure features like we have in our case. So with this, we need to do the parameterization of these energies in the hopping rate using a DFT. So that's the work that Ahmed and a collaborator has done for the gold Syria on STO system. We look at these things by the species that is deposited. We're depositing gold in Syria, and we consider Syria molecules in this particular case. These things might land on, in the beginning, they land on STO surface because you don't have anything deposited yet. But later on, when you cover the material or the STO with your phases now, Syria or Syria and gold, this AU can land on gold or on Syria. The Syria molecules can also land on gold or Syria. So we have these 4 situations to look at hopping energies and also binding energies among them. So we did these simulations by DFT to calculate the energetics. The bonding energy is just the bonding energy. You compute it from the structure. The hopping energy, you have to use the so-called nudged elastic band calculations. It's a scheme that looks at transitions, basically, between states. And you capture the energy difference between the initial and the so-called transition state when the system is kind of jumping from one state to the other. This is just illustrating this transition here. You have, if you think of this red curve as like an energy landscape, your hopping species just go up here, and what matters is the difference between this state and the initial state. That will be characterized as your hopping energy in this case. Again, we compute this for gold on gold, gold on Syria, and then Syria on gold and Syria on Syria. And then we compute it also for both on STO during the early growth in there. So this is just a cataloging of these energies, barriers and bonding energies for these things. When during the growth, you're going to have the hopping atom having also other atoms of different and molecules of different species. We do interpolation based on these combinations that we have. That's kind of like a reasonable approximation for this. If you're depositing gold only, you're going to see this red movie, gold on the substrate, and a layer is completed. You deposit in patches, and then the atoms self-organize and go in layers until they fill the surface. If you deposit the ceria, it does have the same, it behaves more or less the same, like this one. So this is a standard or the classical single phase film growth simulations that people have done. In our case, we're actually depositing the gold and the ceria together, and you end up with something like at the bottom here. You have them deposited by a certain mass ratio. So at the end, the collection of the red and the blue masses is what you have added to the system. But the simulations give you or tells you about how the red is distributed within the blue phase here. The red is a gold phase. This is just one layer, the very initial layer in the system. The next layers are going to recognize that you have these islands of gold in the blue phase here, and then the gold is going to attract gold and grow vertically here, and that's what we call the vertically aligned nanocomposites. Gold sort of attracts gold to grow in that vertical thing because of thermodynamics. It likes to phase separate from ceria. It doesn't with it, so it has to go to gold and grow these things vertically. Actually, anybody who knows phase thermodynamics and kinetics of island formation would actually predict that these things are going to grow vertically like this from the beginning. So that's the growth of the pillars, the red phase here. In the matrix is also growing concurrently or simultaneously, but it is suppressed in order to view the pillars and their self-organization in the matrix, as you see in this movie. The next thing is to look at the deposition parameter effects on how these pillars self-organize. The self-organization here means the density of the pillars, the size of these pillars, and whether there is a particular order on the surface, like a pattern, like a square pattern or a hexagonal pattern, a random pattern or a quasi-random pattern on the surface. That is sensitive to the pulse, the amount of mass you deposit per pulse, the pulse rate, the substrate temperature, and so on. So this is like a catalog of the morphology dependence on amount of atoms per pulse versus temperature, and also the from high and low number of atoms per pulse in the temperature and frequency space of the pulse, laser pulsing, basically. This doesn't show much as far as a conclusion, but these figures here summarize the data that you show on that figure of the morphology. Density as a function of temperature for various rep rate in here, and they are plotted for pulse magnitudes of 150 atoms, 100 atom, and 50 atoms. And then the pillar size on average here as a function of temperature, again, for these deposition parameters again. So this is a lot of data condensed on one figure. The most important thing to observe here is the following. The density kind of increases with frequency increase in lowering the temperature. And the pillar size behaves of the opposite way. Density means the number of islands that form in the beginning, they become many or they become a lot. The number becomes higher if the temperature is low and the rep rate or the deposition rate is high. The reason for this is that at lower temperature, atoms don't get a chance to diffuse much, and every small number of atoms in a small neighborhood will just aggregate, and you have a lot of these patches on the surface itself. As a result, you get thin pillars of larger density, and of course, the size gets behaves the opposite way of the density because you have fixed material in there. In the analysis of the size, we actually found that the size average size does not scale the density in the proper way or in the ideal way. Ideal way is that the pillar size will times the density will give you the volume deposited, and the volume you control during the deposition process. But we found that this scaling doesn't hold, and the kinetics, there are kinetic effects that interfere, and there will be atoms left in the bulk, the gold atoms left into the interior of the Syria matrix, and those kind of, you take a volume out, disperse, hide it somewhere in the matrix, and it kind of makes that relationship deviate from ideal. So this is like a scaling of the diameter with the density that is deviating from the ideal exponent of 1/2 or minus 1/2 because of kinetic considerations. We looked at the self-organization in these pillars in terms of the correlation, the spatial correlation of these pillars on the surface, and we got something that looked similar to what the correlation that has been analyzed for an actual experimental micrographs here. Especially, we get, from these correlations, we see the higher density of these 2-point. This, you can think of it as a 2-point density as a function of oriented distance. And the peaks here represent directions where you get more correlations. So it's an indicative of how the pillars are organized on the surface itself. The zero distance here, or the core part of this correlation, has to do with the fact that, or correlation of pillar material within the same itself. So you're always within like a 2-pillar diameter region in the middle here, if your pixels are so tiny and the pixels take black and white character of the matrix versus pillar in this particular case. So we got nice agreement with the experiment, except that pillar sizes are kind of slightly off compared with the experiments. And we know why, because in these simulations, we're actually missing the elastic effects in the simulations. This brings me to the next modification of this method, which is, if we have multiple materials and there is a significant mismatch in lattice parameters and so on, and there are elastic strains coming due to this match in the system, how does this elastic strain influence the diffusion and self-organization kinetics on the surface? In order to answer this question, we need to do two things. Number one is to capture the strains. And number two is to capture the strain effects on the kinetics by looking at how the strain impacts the hopping energies and binding energies on the surface, because the combination of those two energies contribute to the hopping rates on the surface. So there is an elastic problem to solve, and then a reparameterization of the energetics on the surface as a function of the strain state at the surface itself. So I'm going to skip a lot of details here, but there is a good mechanics problem to solve with this. And this mechanics problem has to do with capturing the details of the strain, elastic strain, within this heterogeneous system. So there is a mechanical boundary value problem to solve in this regard. We set it up in terms of deformation kinematics and stress equilibrium. I'm going to skip the details here, but in order to do this, we approximate the morphology of the pillars from this atomic picture, which is the output of the KMC simulation, into something that looks like elastic continua. And you have irregular shapes, of course, but the pillars is a material and the matrix around it is a material. So we go from the atomistic pictures to this using very sophisticated geometric analysis of the atoms in this particular case. That enables us to solve a boundary value problem of elasticity in a heterogeneous system. I'm going to skip it here. This elasticity problem, it consists of three types of equations: the kinematic description that I put in the beginning here, and the stress equilibrium, and some constitutive laws, or Hooke's law, you might call it so. And we cast all of this in the form of a boundary value problem that we solve in our case using fast Fourier transform method, FFT methods. So I'm going to skip the FFT details because it's standard, and show you how the strain looks like in the heterogeneous material system. First of all, before we get to this, I'd like to just draw your attention to the fact that this film system is infinitely extended, or not infinitely, but extended in the plane of this film to large sizes. On top of the film, there is empty space or vacuum or something like that. This problem does not lend itself to fast Fourier transform solution in the 3 dimensions. We can do periodicity or assume periodicity only in the 2 directions containing the plane of the film. So what we developed is a so-called RVE formulation of this elastic boundary value problem that take into consideration that the fact that we don't have translation invariance of the volume that we're interested in the 3rd direction, which is perpendicular to the film itself. But we did this formulation in preparation for FEM type solution, but then my student figured that FFT would be a very nice tool to use in this. FFT works for periodic domains, basically. So we had to artificially add a material, a soft material at the top here, in order to make this domain available for FFT solutions. So it takes a little bit of experimentation with defining this very soft medium on top of the film to get the right stress. So it takes a lot of benchmarking with known solutions and so on. Eventually we have it. And what you see here is just a sample stress calculations over a cross-section of the film, a vertical cross-section here, and a horizontal cross-section here. They test nicely with known solutions in the literature for this idealized cylindrical pillar in a matrix. And we take this to solve the more complex problem of having these irregular shaped pillars now in the matrix. And we were able to capture the strains in a very nice from them. What you see here is some elastic solutions for morphologies that have been grown by Monte Carlo at different temperature, 300, 600, and 900 degrees. At high temperature, you get a lesser number of pillars of larger size. At lower temperature, you get high density of pillars of smaller size. That morphology does impact the strain directly, and we're interested particularly in the strain at the surface of these films. So that's what you see in the map. It's projected here. That is a part of the strain field that will interact with the diffusing atoms. The atoms that deposit on the surface will see this kind of strain on the surface, and the strain, being a local quantity now on the surface, will alter the hopping energy and the bonding energy depending on the magnitude of the strain at various locations here. So we're expecting to see a significant effect of this if the coupling between the strain and the hopping and bonding energies is significant. So back to the parameterization again. This is the hopping energy or the energy that controls the hopping rate. This energy has a free hopping isolated species on a surface, and then bonding at the beginning, initial and final sites. Both of this hopping energy and bonding energy do change as a function of strain. So we write this dependence on the strain as no strain value plus a first order correction of these energies with respect to the strain. This strain is a tensor, so this is a stress-like quantity. It's a tensor quantity, also this variation. And we compute these things from density functional calculations. So we go back to the parameterization business. We enforce tensile or compressive strain in one case, positive shear and negative shear in another case. And we look at the various combinations, again, gold on gold, gold on Syria, Syria on gold, Syria on Syria, under various levels of strains. This is an incredible amount of DFT calculations. And I have to commend Ahmed for actually being able to perform this very large amount of DFT calculations to look at the bonding energy, strain effect on bonding energies and hopping energies on a multi-component system like this for just the parameterization. He computed as a bonus the surface energies as well. So that's the surface energy as a function of strain. It shows that it does vary. It is more sensitive to the tensile and compressive strain than the shear strain. And he computed the dependence of the energies, the hopping energies and the bonding energies on the strain. It varies from, he spans a strain from negative to positive values, that's compressive to tensile, and also shear being from negative to positive values. The uniaxial or the normal strain components are more effective in changing the bonding energies than the shear components. He repeated the same thing for the hopping energies and cataloged, again, the dependence of these energies on the strain for both normal strain and shear strains, both positive and negative, tensile and compressive, and positive and negative shear, here for the diffusing species on different surfaces and so on. And we got all of this. He's currently in the process of putting this in the kinetics. What you see here is an old calculation that he has done to test strain effects on the kinetics of growth. And he did found in here, there was he was kind of putting in a crude approximation of the strain effect on the hopping energy, the overall hopping energies. And we did discover that there is an impact on the shape of the pillar. You see here a lot of roughness on the pillar surface, but these pillars on this side here are actually more straight. Right now, he's in the process of integrating all that DFT into the Kinetic Monte Carlo, the elastic solver, the DFT parameterization, and the KMC techniques together. That brings me to my final view graph here for this framework. It works nicely for understanding the kinetics of this growth. It is being enhanced currently with the elastic solutions and DFT parameterization that depends on the strain and so on. And we have used this thing to do so-called strain engineered film growth by looking at templates. These are actual growth morphologies, interrupted growth to put a layer of one phase and then resume the growth again. And the pillars kind of know where they were in the past, and they grow on top of each other. He actually simulated this, and we found that the KNC also kind of recognizes where these things are. In order to do this, you have to know the strain, because the pillars under this green layer communicate with the newer ones through the strain effect. Without the strain effect, you won't know this. These things will not know that there were pillars grown before in the system. We're also making another improvement in this. The pillars do have irregular shapes, as you see here. And these irregular shapes are kind of associated with curvature, and the curvature gives rise to so-called capillary effects. in macroscopic or macro scale elastic materials, we don't care much about capillary effects, but in nanoscale systems, the capillary effects are actually important and they have an impact on the strain in the system. So this is also being integrated currently with that framework. With this, I'm going to stop and see if the audience have any questions.